what is it is about today lectures. So I would like to share with you some recent research from recent years, in which were based on machine learning or similar approach. And the first concept I would like to remind you is concept of physics-based modeling versus data-based modeling. So probably you discussed it last time with Hrvoje. I believe that he should mention it. That the idea behind research based on physics-based modeling is completely different from data-based modeling. So just to introduce these two concepts, I believe you know these two concepts, but I want to just to remind you about it. So let's analyze very simple exercise. So it is very simple tasks of physics task. I think that it is from like from basic physics course problem. And this example of football may be unrelated to this topic, but it is quite close related. In fact, it can be. So if you have such a issue to solve about trajectory of ball, about speed of ball, and if the ball is going to go to goal bar or not. So if you want to use traditional physics-based approach, you should solve some equations, and these equations. So if you had a basic physics course, you should solve this problem quite easily, and this is about considering some law of gravity and some law of dynamics. And based on these laws of physics, you have to design some equations and solve these equations, and that's it. And it is not very difficult, but still, probably these football players don't do it. They don't think about physics during football match. So how they do it, if not in that way? Because this is like this is a way which is maybe the the most comfortable for such a nerd as me, as physicists, but for sure these soccers don't do it. So our approach can be physics-based. It is kind of top-down approach, in that meaning that we have to know laws of physics. So we have to know mechanisms of and processes which are involved here. And starting from this understanding of this world in this physical way, we solve these equations and just calculate the solution. And completely different is bottom-up approach, in which we have some data, and based on this data, we just develop and maybe guess a solution. So how it works in the case of this football? So if you try a lot of times, many times, to do the same. So if you try really like 10 times, 100 times, 1,000 times to kick a ball, and after this kicking, you can see results. So you can see the trajectory of this ball, the speed of this of this ball. So you gain some experience, and your decision during this kicking later on is based on this experience. And in this specific situation, this experience is based on data which are collected by the player through whole his life and whole his training. So such a football player collects really a lot of data, because You know that if I go to the outside and kick a ball even 100 times, I'm not very good soccer. So to be really good, you have to do it many times, like thousands times. You have to train a lot. So you have to collect really big, huge data set. And this data set is stored somewhere in your brain. And then when you have to use it in a specific situation, you just use it. And this experience is based completely on data which were gained before. So this is a completely different approach than this physics-based when you just consider rules. Okay, but in fact, in science, we use the third way. So it is very what is called hybrid approach is used very often, and it is a situation when you can integrate data-based modeling, so you can integrate approach when you solve problems using only data, but you don't want to forget about laws of physics, so you want to adjust solutions to be to agree with laws of physics. So this is hybrid approach, and this is the most common. So these examples we are going to analyze today sometimes are can be classified as this hybrid approach. Okay. As you know from the last, I think, lecture, there are really a lot of machine learning algorithms, and you can see on this picture only some examples. So there are much more algorithms than you can see here on this picture. And these algorithms can be classified as so. There is quite a lot of classifications, but some classification can make the groups as, for example, regression algorithms or deep learning algorithms, as you can see here. And these algorithms are used in three, I think that three basic ways. So the first way is supervised learning, and you have to use specific data sets to use this supervised learning because you need to have labels in your data set. So some data are features, and you also need labels. And it is quite difficult sometimes to find such data sets, but it is quite common, and probably the most common way of using this machine learning. The second one is unsupervised, which is much more fancy because you can classify and cluster data without any labels. And the third way is reinforcement learning, and it is when you apply, it is the most fancy because you apply in this approach, you apply a few algorithms, and the final algorithm learn from mistakes. So try to solve problem and improve itself individually, like itself, when make some mistakes. So this is the most advanced, this reinforcement learning, and I don't think I don't have example of such kind of machine learning. It's not that common in science. I think that in technology it's most common than in science. Okay, so also in general, we have these problems which can be solved by these approaches is classification, regression, clustering, or ranking. So this is typical problems which can be solved by machine learning. And I think that for us, the most interesting is regression, because it allows to predict some values, probably sometimes classification in marine science is also quite common. So, yeah. Okay. Let's go further. So if you want to use any of these algorithms which you have seen on the previous slides, you can apply any kind of data, and the algorithm really doesn't care what kind of data you feed to it. So you can take anything, give it to algorithm, and you will receive some output. So this data can be financial, some health data, biological, weather data, social media data, whatever. So there is a lot of algorithms. They are tested in various areas, not exactly in earth science, not always. But if you want to really use in earth science, there are some specific challenges in this discipline due to quite complexity of environmental systems. So as you know, environment is very complex system, and you have a lot of interactions between processes which you can observe, and between parts of this system. So the complexity is quite high. And this is one of challenges, but also there are other challenges. And let me see what is okay. So the most important challenges, this here you can see from a paper from 2020 which summarize these facts, but what is the most important from my point of view also, it's that in earth science we don't have a lot of benchmark data. And what I mean benchmark data, so it is a well prepared set of data. For example, it could be data of wave heights, or of some coastal processes, of shorelines. So I would like to have some set of data which is very well described and which is open for everyone and can be used to compare performance of various algorithms. So I think that Hrvoje during the last lecture probably told you about this IRIS dataset. So it is very classical, or probably you've heard about in some other situation. So this IRIS dataset is very popular and very common benchmark data. Everyone can use it, and everyone can try algorithms and can compare outputs of algorithms using the same dataset. And we don't have a lot of such benchmark data in marine science. So this is the first gap. And it is important because I want to be sure that output which I produce makes sense. And of course, I can use my own data, and everyone does it. But sometimes it would be very good to compare performance of new method to other methods. So it is very important to construct this benchmark data, and I think in the near future it will happen. But for now, it's not it's not a lot of these data sets. Also, another problem, another challenge is that in oceanography, we have really a lot of data. You've seen the Copernicus system, and Alfredo, I think, show you how to obtain a lot of really free big data sets about almost everything you need in physics, at least. But most of this data comes from modeling. So these are results of simulation, of numerical simulations. And in other disciplines, these algorithms which we can use. So in other disciplines, these algorithms are used to the real world or observational data. So this is a little shortcoming of our situation, that we don't have really a lot of observational data. Also, if you even have this observational data, they are in various standards. They are also very often with labels. So we don't have labels to our data. So it is difficult to train data sets, to train our algorithms because we don't have these labels. So I mean, for example, that we have information about. So this is problem from last week. I tried to solve that. We have information about topography of the shore, of the seashore, but we don't have labels. What kind of shore is it? So is it cliff or is it flat shore? So it is not so easy to classify, to prepare this training data set very well classified, that we can learn algorithm to forecast the type of shoreline after that. So this is a kind of challenge. Also, but this is easy to solve, but there are some more difficult challenges, problems. So the first problem is that in a datasets we use, there is not a lot of extreme events. And if we want to forecast, for example, weather or sea dynamics, the most important, very often the most important for researcher is to get know something about extreme events, for example, about storms, about extreme waves or something like that, because it is it has the biggest influence on some other things. So if we don't have these extreme events in our data sets, and we don't have because these extreme events are very rare. So even if we have, for example, 1 year, 2 year data sets, so we have really a lot of data sets. For example, I think all the time about waves, sea waves, because it is what I work with last time. So I can have like recording of wave buoy from 1 year, 2 years, 3 years. And in this recording, I have like 10 storms. So it is not a lot, but in the same time, I have really a lot of examples of calm weather. And very easy sea state. So if I don't have a lot of these extreme events in my data set, algorithm is not able to learn about how to predict, how to recognize these extreme events, because algorithms to get some knowledge about patterns, about processes, algorithms needs really a lot of examples. Like this soccer player needs a lot of repetition of kicking a ball. Algorithms needs a lot of examples of some situation to learn about it. So so this is quite a problem, that we don't have a lot of extreme events. And the most maybe important thing, maybe it is not a challenge, but it is something you have to understand, that this data-based approach has this limitation, that it answers questions about what is happening and how is something happening. So about some processes, how it goes, and about some patterns, about some rules, about some classification. Also, algorithms can predict what is going to happen in 1 hour, in 2 hours, in 1 year. So everything is possible, but algorithms cannot answer questions why something happens. So when we think about rules which governs the behavior of some system, such approach, this data-based approach, doesn't give us any answers. So that's why we cannot have this hope that these algorithms explain why the solution is like that. It is just like that, and we don't know why. So we just obtain some solution, and it is from black box, like gives us this solution. And if we ask, but why, we don't have any answer. So that's why this physics-based or process-based science research is really, really needed, and we will still use it in the future. But in the same time, simultaneously, we will use this data-based approach, and we will solve a lot of problems in science, not only in science, but also in engineering, in technology, using such approach. Okay. So let's take a look at what is happening in scientific world. So here you have results from Web of Science, and it is from yesterday or maybe 2 days before. I just checked it before this lecture. So we have 1,200 results for a question which is like that. So question is keywords: oceanography, marine, ocean, or sea, or coastal, or coast. So such areas. And in the same time, machine learning or artificial intelligence. So of course, probably there are a lot of papers which are about this approach. So use this approach and don't have these keywords. So these papers are not in this classification, which I present, but it is just to to have some intuition about how it works. So please have a look. It is like from 2020, I think. So this is the 5 years ago. It started to develop really really fast. So before this 2020, there were, of course, some papers about it, some scientific research, but not such a lot as from 2020. And what is interesting, so maybe the next thing is that here I show you only top 10 of areas. So of course there are more areas of research, but I just wanted to show you the top 10. And the most important group is engineering. So it is because as I told like 1-2 minutes before, that these methods don't explain the laws which rules the environment. So this is mostly about applications. So these methods can be very useful in some technical specific applications. So that's why engineering is the most important group here. Also, the important group is, so in this environmental sciences, ecology, I haven't checked, so I don't know what kind of papers are there. Also, we have something like marine freshwater biology, telecommunications, things like that. But we have remote sensing, which is very important group because, as you know, from remote sensing, from satellites data, we have really, really a lot of data to use. And as we thought some times ago, to use machine learning approach or data-based approach, you have to gain a really huge experience, and experience equals data. So if you have data, you can use this approach. So in remote sensing, we do have data. And also imaging science photographic technology. So also we have a lot of video data. So this is about research areas, just to make you to give you also this intuition where it is really important and fancy now. And what countries? So this is only just to show you how it changes. So researchers, of course, from China and USA are in the first row. But what you can see here, it's from 2023, this picture. So it is now it looks a little bit different. So we have here China and USA and Australia, Canada, South Korea, and Europe in general. And this year I just checked, and it occurred that we have quite a lot of papers, so 65 papers of India this year. Up to this year. So when we consider only top 10 countries in which such research is popular, we have India as newcomer, and I just wanted to check what happened during these last few years. So this left picture is about number of papers in specific years, so 2021 to 2025. And India is new one in this top 10. And Germany was in the top 10 2 years ago and now isn't. And what happened? So we have in Germany the quite stable level of these researchers, but it is still lower than in India. And in the middle, I put Spain just to compare that something is happening also there. So it is just to show you that where this research is popular. Okay. So now I'm going to go to quite specific cases, and we will go a little bit deeper into some very specific research. Of course, we cannot cover all what we can see here, but I just choose, I think that 3 of these groups. And I also have from previous years also some other cases. So let's see what is happening here. So this is the main aim of our meeting today, to know what is happening in the scientific worlds. So let's make this revision. Okay, so the first group is about processing images, and we will try to understand how it is used, these methods, to forecasting shorelines. So the position of shoreline, and the paper we are going to analyze is from 2021, so 4 years ago, I think. And this is from Netherlands, a group from Netherlands, yeah, all of them from Netherlands. And they considered how traditional versus machine learning methods works. So traditional, they mean these physics-based methods. So we have this comparison of these 2 approaches, which I mentioned, how these approaches work for forecasting shoreline evolution. And they use satellite-derived shorelines. So this is shorelines which are from kind of images. So we have this, that's why probably it goes to this group. It was classified to this group by Web of Science. Okay. But before we go deeper into this specific paper, I would like to show you another paper, which is from 2007, I think. Yes, 2007, received 2009. So I would like to show you where it is on our timeline. So 2007 is somewhere here. I'm not sure you can see my pointer, but 2007, 2009, as you can see, know a lot of papers using machine learning. So it is completely classical paper, which try to calculate these shoreline changes on the very similar data. how this process of prediction of shoreline can be organized. So maybe firstly let's have a look on this graph. I will try to make it a little bit larger, maybe. Oh, I hope you can see it. Oh, no. So you can see shoreline position here, and this black line is model. So it is calculated by model, and this is physics-based model. So this model is based on equations and of laws of physics, some real processes. And also we have data. So there are some information about these shoreline changes based on data, based on some visual data. And these data, of course, are collected with errors. So that's why, like always, like all measurements, also model data are with errors. So this is like normal. So as you can see, this prediction is quite in the bounds of errors. So it is quite good prediction. And what is important, the data which are used for calculation, so the input data to the model are data about wave height. This data on this upper panel are input data to this model. And how to construct such a model to be able to calculate this shoreline evolution, let's see. So what is important, how we can do it? So it is process-based, like physics-based or process-based. It is like the same meaning. You have to consider this the most important processes. So you have to consider, I'm not sure if you are familiar with sediment transport, maybe some of you, but you have two kinds of sediment transport, of sand transport. One kind is when sand is transported along shore, so it is parallel to shoreline, more or less, we can say. So it is connected with wave approaching the shore with some angle. Lose energy, and this energy is, it is very simplification what I'm telling now, but okay, let's simplify it. So energy is lost, wave energy is lost, and it is transformed into current, so the flow of water, and this water flows in parallel to the shoreline, and sand is transported. So this kind of transport is longshore transport, and when this transport is disturbed somehow, you have some sediment is accumulated, can be accumulated, and some sediment can be lost from the specific point of shoreline. So that's why shoreline move. So this is the main reason of moving of shoreline. So this is the first thing. Then and another thing is cross-shore sediment movement. So we have exchange of sediment of sand between beach and offshore. Another kind of processes, and these are completely, maybe not completely, but different processes. So this longshore transport, when sand is transported along parallelly to shoreline, and when sand is transported in cross-shore direction, these are completely different processes, and they have these processes should be considered in these models. And also we have some natural driven sediment input outputs, because we have wind which transport also sand from beaches and things like that, and also can be human driven. So all of these impacts should be considered. So as you can imagine, such a model can be quite complicated when you want to calculate using such approach the position of shoreline, for example, in 1 year from now. So it is quite difficult to consider all of these processes. But of course, we can try to do it, and then we should use some models. And these models here are put in the ranked by complexity. So the most complicated models are 3D hydrodynamic models, where you consider you had some lectures about modeling, so you know. So you consider 3D grid, and you calculate water movement, water dynamics using this 3D grid. What does it mean? That in each point of grid, and if you want to have good precision, good accuracy, you have to use a lot of grid points. So this you have a lot of these points, and in each point you have to solve some equations. So if you have dense grid, 3D grid, you have to solve really many equations, the same, but still many times you have to repeat it. So it is very complicated in the sense of computational effort. But this is something we really like. It is the best what we have in the meaning of physical based modeling. So these are these 3D models. They are quite developed now and very useful, very common, popular in very engineering approaches. So situations. So we are like as a society of researchers and engineers, we have these tools really well developed. Another way is to use to reduce this complexity, and we can use 2D coastal models. In coastal area, it is possible. So we neglect this third dimension. So we neglect depth, and we imagine the ocean that this is flat. So each computational grid is like kind of vertically averaged, and complexity is smaller, but there are some problems with it, because when we neglect this third dimension, we neglect a lot of processes. For example, vertical exchange of water, these vertical movements, also the profiles of temperatures, of vertical profiles of temperatures, of density. So a lot of processes and features of water we neglect using these 2D coastal models, but still we can use it to calculate some shoreline changes also. And the last approach, we can use empirical models. What does it mean? That in fact we forget a little bit about all these processes which we have on the left side, and we think only about data. So this is kind of data-based modeling, as we discussed previously, but it can be, it doesn't have to apply these fancy modern machine learning methods. It can apply very simple linear regression, for example. And you can imagine that, for example, you have Google Earth or some other source of satellite data. You can see where the using this satellite data, you can see that in this year the shoreline was in this place, and previous year it was 2 centimeters moved, and in previous years it was also moved. So you can detect the position of shoreline in some years, and you can decide that, okay, so I can see from these pictures that this shoreline is moving towards, for example, 2 centimeters per year or 1 centimeter per year. So you can predict, and it is linear regression. You can predict the position of shoreline next year. So this is also empirical model. Of course, it is with there is quite big errors in such approach when you have limited number of data and very limited methods. So this linear regression assumes that it is the movement of shoreline is the same length each year. So 2 centimeters each year, for example. So it is linear, but of course in nature it's not linear, so it is very, very simplified. So we have we have these models, we can use it, but there are some shortcomings of all of these approaches. So even these 3D models, which are the best we have now, require really big computational effort. So if you want to create a very long-term shoreline prediction, or any other process prediction, it is really difficult because of computational effort. And also because of errors which can occur. Because if we predict for example, 1 week or something like that, it is these errors are not that big, and these errors are because of each model has simplifications and some assumptions. So these assumptions produce some errors in outputs. So if you create this output for many years, so long term, these errors are quite big. So the same situation with 2D coastal area models. As I told you before, we have this a lot of nonlinear processes which are simply neglected when you neglect this third dimension. So this is like that. And let's have a look this paper which we had. I show you this one, physics-based modeling, classical approach. So as you could see, they perform quite well, and let's see how they do it. So this is how they do it simply. So maybe I can make it a little bit larger. So the basis of model is a classical equilibrium equation, and the input data are video derived time series of weekly shoreline positions. So as you can see here, these barbs are this data, but oh, sorry. Oh, I have this. So we have this video derived time series, but of shoreline position, but it doesn't mean that this research is data-based. So data are really used here, but the research is still process-driven. And I would like to show you the difference on this using this example. So the authors will use this time series, but in very specific way. So how they use it? So the data are from Australia, and they have this time series of weekly shoreline positions. So as you can see on this picture, and then they create some model, and of course model is based on some assumptions, as model physics-based model always has assumptions. So these assumptions lies like that a longshore sediment transport doesn't have gradients. So it is uniform. Of course, it is a simplification. Also, a model is forced by waves and tides. So that's why we can see these wave heights on the upper graph, because these wave heights are input data to this model. What also is important, that some other process-based assumption that the volume of sediment is conserved. That means that if 1 kilogram of sediment is moved from one computational point to the next, it is still 1 kilo. So it cannot be lost in the process of calculation. So this is the next assumption. And they develop one specific parameter, and it is this parameter is called omega. It's fall velocity, and they calculate this fall velocity. It is output, let's say, output of the model, this fall velocity, and it is based on parameters of wave. And they assume that erosion occurs when this fall velocity is small, and accretion, so accumulation of sand, occurs when this velocity parameter is high. So what does it mean that it's small or that it is high? They need some criterion, so they introduce additional parameter, which is called omega 0, and they compare this fall velocity to this specific number. And how they guess this number? This is the most important thing here. So to guess this number, sorry, because you know, when they want to know that this shoreline move up or down, it is erosion or accumulation. And to decide if the points should be moved to higher values or to lower values, they have to decide based on some numbers. And this number, this omega 0, is derived by this video data. So the model is calibrated using this data, this known data. So they calibrate, once again, they have some data from video recordings, and they calibrate, they guess the threshold value based on real in situ data. Maybe not in situ, but video data. I hope you understand this point of this research. So the most important for you is that approach is based on physics. So you don't have to understand all these assumptions, because it is not the really aim of this meeting today to understand all these details. Maybe it is interesting for people who work with this coastal protection, something like that. But in general, understand that there are some real physics-based assumptions, and using these assumptions and using some equations, we have some equation, some model, and in this model we have some parameters, and this omega 0 is parameter, and these parameters should be calculated or should be guessed based on some data, and this process is called calibration. So in physics-based approach or process-driven approach, you also use data. It is not that you don't use data at all. So you use data, but these data are used for calibration. And when you have this model once calibrated, you can use it all the time. It is assumption. So it works like that, and this is very classical approach. And let's go further. So then, of course, their results are quite good. These errors of prediction is quite small, so they are satisfied in this approach. Okay, but what is important here, that this parameter, this threshold value omega 0, is it's about 4 here, and it's local. So it works for this specific coast. I cannot take this model and use this for to other kind of coast. So I have to reuse this model. I have to calibrate it once again. So this is important thing. Okay, so now let's go to. So this paper was to explain you the traditional approach, and now we have paper which test different kind of approach. So this is again the same paper we focused like 10 minutes ago. Traditional versus machine learning methods. So they compare these traditional methods with some new algorithms. And let's see what are results. Classical methods used in this paper are like that. So first method is linear regression. It is based on linear regression. It is called OLS here, and it is something similar as you can take this Google Earth data or any other satellite data from 1 year and the second and the next and the next, and compare these situations and you can have, for example, 10 pictures and have some results based only on this. So we have this OLS. It's quite statistical, I can say, method. Also some other method, ETS. It is based on analyzing seasonal trends. The next very common method is ARIMA. It's autoregressive integrated moving average. And this is very statistical method. So I'm sure you know this method from statistics. This ARIMA and ETS have some parameters, P, D, and Q, and these parameters were estimated automatically by authors using some package. So these were classical methods which were used, and these methods are compared to some machine learning methods. So most of these methods are based on neural networks. So I think that you have some idea of neural networks, probably from Hrvoje lecture, I hope. But these neural networks are modified, and we have really a lot of various algorithms based on neural networks. So we have here used in this paper, we have FFM, so it is feed-forward network, LSTM, long short-term memory. Also, we have CNN, so this is convolutional neural network. It is kind of deep learning. So these three methods are based on neural networks. And also we have, also this deep RR, autoregressive recurrent neural network, so RNN, it's also neural network. So most of them, I think, I based on neural networks. So they tried this 1, 2, 3, 4, 5 algorithms, machine learning methods, and 1, 2, 3 algorithms, classical methods. And what they achieved, so results are like that. I'm not sure I have these results here. Oh, I have. Results are like that most of these algorithms give good performance in general, and but the main conclusion is that there are some advantages of machine learning above traditional methods, but this is not very big. In this, what is important? So important fact is that, just to conclude this part of lecture, important is that, as you remember, most of research, let me come back, most of research using machine learning methods are in engineering and also imaging science, but this is here it's similar. It's also coastal engineering, this paper we discussed now. And even if we have quite good group and the paper is quite new, so it is a novel approach for sure. The results are not very much better than this traditional. But what does it mean? We have to develop it more, because our traditional methods, like based on models, have also a lot of limitations in this long-term forecasts. So we do need these data-based methods, these new algorithms, and these algorithms should be just adjusted and improved. So now we have in the situation that we have similar accuracy in this approach, in these two approaches, but the Society of Researchers believes that it can be better in the future. So now we are in that moment of development of this algorithm. Okay, let's go to the next paper, and I will try to be short, to make it short. So here we have from oceanography, we have paper which is I chose because of, look who is an author. It is Adam Gauci. So for some of you, it's your teacher. So this is paper for 2024. And it is about predictive modeling of sea debris around Maltese coastal waters. So of course I choose it because of you. A lot of you are from Malta. So just to quickly to look at this paper, what I have here. So we have this sea surface debris, which are mainly made of plastic. And here in this paper, this hybrid approach is proposed. So not only machine learning, but also physics-based Lagrangian model. So Lagrangian model, it's kind of a numerical model which goes towards one specific chosen particle. So it analyzes the fate of one particle, which the road, the trajectory of it, and they just combine these two approaches, and this is kind of hybrid modeling, and results quite accurate 24-hour prediction of sea surface debris movement. So quite good 24-hour prediction. I think that it's good result. So this is one of paper I wanted to show you. And another paper is it's also not so it's mine. So I just wanted to show you my research, what we did some times ago. So it is also forecasting, but forecasting of sea waves, and it is short term. So as in the previous paper discussed here, this predictive modeling, it was forecast for 24 hours. We were able to forecast wave height for 6 hours with good accuracy. So I don't know if I want to say you the details. So, but also we used LSTM neural network, and it was the best. And it was similar. Maybe let me come back to this previous paper. So here they used LSTM and RNN and compare it to, and also other methods, but we used RNN and LSTM, very popular neural networks. And we also compared it in our paper to ARIMA, autoregressive integrated moving average model. So we did pretty the same thing, but the data was of course different, because here in this paper data was about shoreline position, and in our paper data was about wave height. So as you can see on this picture, you can see the wave buoy. So wave buoy measured the wave height, and we wanted to produce the forecast based on only on this data from wave buoy. So of course, to predict wave, you can use physics-based model, for example, SWAN model or VAM model, to produce forecast of wave. You have to solve a lot of equations in many grid points. And of course, it is like state of art for now, and it is not very difficult to do it, but we wanted to check if we can predict a wave height using only data from wavepoint, so not no physics at all. So it is not a hybrid approach, it is purely data-driven approach. So what we did, we had to adjust the architecture of this neural network. We used a lot of examples of hyperparameters, so it was the optimal configuration. But of course, it is one that we guessed it. This optimal configuration, we had to try a lot of many of configurations, and it was done automatically. And we were able to, as you can see, we were able to predict some this waving with quite good accuracy. So it is not very difficult to do it. Okay, so these are some very specific errors, so I don't want to go to details. So these examples, which we considered now, these three examples, so examples of shoreline evolution, of debris trajectories, and of wave heights, are quite similar because it is prediction of some processes. And algorithms are very similar also. So the same algorithms and only different data sets. So algorithms don't care about what kind of data we feed, as I told, and we just obtain some results using different data sets and the same algorithms. The important thing is to have optimal architecture, so optimal number of neurons, optimal number of hidden layers of neural network. And if you do it, if you use properly prepared training data sets, you can generate such a prediction. It's not how to say rocket science. It's quite easy to do it. But I would like to just to end, I would like to show you something completely different. And this is from marine biology, because I think that it can be more interesting to you, and also it is different kind of research. So we have this marine biology, and the topic is automatic identification of phytoplankton. So as you know, when you have pictures of phytoplankton, or you can observe this phytoplankton using microscope, it is difficult to recognize the species. And as far as I know, it works like that a very experienced person observe the species using microscope and classify using own experience. So one of my colleagues at University of Gdańsk do it for many years. She is very specialized in it, and she can just recognize using her memories, her experience. But the topic is how to do it automatically. So we want to have this identification without human. So how to do it, and here we have the specific example how it was done in 2019 in Scripps Institution of Oceanography, and they had a kind of photo camera, I can say, and it was underwater and captures a lot of images of particles floating past by the camera. So this camera recorded phytoplankton and also other particles, and there were really a lot of pictures, and it would be really difficult to have a person who just analyze all these pictures, and especially that the idea was to do it in this in automatical way. So how they did it? This is typical example of supervised learning. Why? Let's take a look on the methodology. So they have this kind of image from camera, and then this image was kind of pre-processed, and for example, here in this specific part of the image, there was something interesting. So the part of image was cut, and this part of image which is interesting, it is called, with something interesting on this picture, it is called region of interest. Please remember this shortcut, this ROE, because it is important to understand the next part. So we have this ROE, a lot of it, with some kind of interesting something on it. And they collected about thousands of such ROE, and all of this ROE was labeled by trained experts. So a lot of works by the real people was done here to make labels. So if you want to use supervised learning, you have to add labels to your data. And in this specific research, these labels were added manually by people. So this experience of the real person was crucial here. Let's see at the results. They had such pictures, and when they gave these labels, they were able to train probably some artificial neural network to classify the other pictures. So it works like that. So this is very interesting research. I think that it can be interesting to you. And this is example of supervised learning. Okay. I think that it is the one of the last slide. I don't want to keep you longer, but let's have a look at this the results. So algorithms use support vector machine, deep residual network. These two algorithms were used, and I will want to check the results. Okay, I don't have it probably here. Yeah, let's do it. Okay, so that's it. Just to conclude, we went through, I think that 4 papers probably. One was this marine biology. It was classical example of supervised learning and classification problem. And 3 examples of predictions based on similar algorithms, but data were different. And one of these approaches was hybrid, and it was this approach from Malta. Yeah. Okay, so thank you very much. Have a good evening. Take a rest, and that's it.